Alright, since we are on a remote learning day today, I'm going to do in this video what I would have done if we were in class, and the first thing we're going to do is go over the homework that you guys had last night. So I have graded those in AB Classroom, and I hope that you can see those answers. I tried to find where to click to make sure that you could, but I couldn't figure it out. So if you can't see them, let me know, and I'll see if I can change that. This question here was missed by almost everybody, and I could imagine possibly this one is a guess. This is a question about marginal cost, and marginal cost is the amount of money that it takes to make one more of a product. So it asks for the best estimate for the marginal cost in dollars to produce the 57th unit of a product. So the 57th unit of a product, we would actually be looking at M of 56 here. And so if you plug in 56, you'd have 56 plus 1 minus C of 56. And so this would give us C of 57 minus C of 56. So that marginal cost there, you would, if you want to know how much it costs to make one more, or the 57th unit, you would take the cost of the 57th unit and subtract the cost of the 56th unit. The idea in manufacturing here would be that the more you make, the less it costs to make each item, because you've got a lot of money in your machinery and your people and all of that. So if they can be more productive and make more things, then the cost per unit should go down a little bit. So that's the idea. Now, there might be things where if you try to produce too much, that cost per unit could go back up. So if this were an option, this would be exactly the marginal cost for 57. But you can see that is not an option. We do see this here with derivatives, but derivatives would not be correct here. So let's think about what we'd be looking at. Let's say that our marginal cost looks something like this. It's decreasing over time. Actually, let me, because it's a little hard, I'm going to say it looks something like this. And so let's say right here is where we've got 56, and right here is at 57. And so we really want to know the difference between these two, but we don't have that. So if we look at our other options and see our possibilities, we could take our cost of our 56 product and divide it by 56. That'll tell you the cost per unit for making 56. But as I said, this amount should be decreasing, so that's not our best answer. Then they also have the cost per unit for 57 minus the cost per unit for 56. That might not be terrible, but our answer here, excuse me, is our derivative. Because if we have C prime of 56, that is our rate of change at 56. And our rate of change in this case would be a cost per unit. So if you're thinking on your axis here, this is your number of units, and this is your cost. So if you take the derivative here, the units for that are going to be cost per unit. So at 56, it'll tell you what the cost per unit is, which will be a good estimate of what the marginal cost would be here. This problem was confusing because of understanding marginal cost. If you still have questions on it, we will look at this in class on Monday if you still need some help on this. This other question that nobody got right was basically the same question. It's also talking about marginal cost, except for this time it's talking about cakes, and it's asking about the 40th cake. You can see the answer choices are basically the same as the others, except for they have used 39 and 40 instead of 56 and 57. And so C, for the same reasoning, is your correct answer for this one as well. So again, if you have questions on that, we can look at it Monday because it is a little confusing. For the free response question, you guys did pretty well on this. There are a couple of things that I wanted to look at. For Most of you guys approximated S double prime of 10 well. I could tell that some of you guys were working together because you incorrectly had negative 1/4 divided by 5, and then you said that that was negative 4/5, which is not right, because there you'd have to put 5 over 1, so it'd be negative 1/4 times 1 over 5, which would be negative 120. And so units are important here. Since we're taking the derivative of the derivative here, our units have to be centimeters per hour per hour. Most people got those units right. What I saw a lot of you missing was explaining this, and some of you did get this right. This is the derivative of the derivative. And so S prime is the rate at which the snowfall is changing, and then for S double prime, that's the rate of the rate. So you would say S double prime of 10 shows that the rate at which the snowfall changes is decreasing by negative 1/20 centimeters per hour per hour. Or you could say it's decreasing at a rate of centimeters per hour per hour. I guess since I put the negative there, I should not put the, since I said decreasing, I should not put the negative there. So it's got to be it's the rate that the snowfall is changing is decreasing. A lot of you just said the amount of snowfall is decreasing, which is what you would use to describe the first derivative. For C, at time t equals 8, the depth of the snow is 48 centimeters. Use the line tangent to your graph. I'm just going to really quickly, this here, it tells us this graph is concave down. And we know right here at 8, we have 45, so this is the point 845. And so if we can find a tangent line here, for 10 wouldn't be too far away. So it wouldn't be exactly the value you'd have at 10 there, but it'd be close. So what you're doing here is you're finding a tangent line. That tangent line, your point is 845, and then you know the derivative at 8 as well is 1.5. So your tangent line should be y equals 1.9 times x minus 8 plus 45. And then so you're just going to plug 10 into that to get your answer. You get 48.8. And this will be an overestimate because you can see that that is above the line because this is concave down. Okay. And for the last part, you want to use your calculator for this. So let me pull up the calculator really quickly. And so for the sake of time, I've already put this into y equals. So right here is our equation that I've typed into y equals for us here. And so if we go back to the home screen, if we do F3, which is differentiate, and we want to tell it y1 of x, since we stored that into our y1, I'm going to put a comma x. If you do this, it will give you the derivative. It will give you the equation of the derivative. However, I really only need to know the derivative at 10. So the calculator can do that for you as well. So you don't have to plug that stuff in by hand. So you'll do such that x equals 10 here. And whenever you do that, you get 23e to the negative 1/4 over 10. What I suggest is you can write that down. They'll take it as an answer. But I suggest hitting the green button and then enter so that you get a decimal because it's easier to write down without making any mistakes. So all you have to write down for this is d prime of 10 is approximately 1.791. And if we think about our units here, D gives us the depth of the snow in centimeters, and the time is measured in hours. So we would have hours here on our x-axis, and we would have centimeters on our y-axis. So our derivative is going to have the units of centimeters per hour, always your unit for your y divided by your unit for your x. And so here, this tells us that the amount of snow is changing, or is increasing, in this case since it's positive, at a rate of 1.791 centimeters per hour at t equals 10 hours there. Again, if you have more questions about that, we can talk about it on Monday. So, let's look at the notes that we are going to look at today. And so, today we're going to talk about straight line motion. So we're going to talk about position, velocity, and acceleration. And these types of functions are used a lot in calculus to apply some of the things that we have learned about derivatives. So, if we have a position graph, a lot of times for our notation, it's not always x of t, but a lot of times it will be x of t. And a lot of the problems that you see, sometimes it might be y of t if you're talking about the y-axis. But I'm going to go with x of t here. And to measure position, you're going to have some sort of time on your x-axis, and then you'll have some sort of distance on your y-axis. So this might be hours and miles, or it might be feet and seconds, something like that. So if we take the derivative, that gives us the velocity graph. And so that's v of t is almost always what you'll see it called. And so when we take the derivative, our units are going to be distance divided by time. So on that y-axis, you'll have distance divided by time. So it might be miles per hour, feet per second, something like that. And then you'll still have time on that x-axis. And then for acceleration, you're going to have the units are going to be distance divided by time divided by time. So distance over time over time. And your x-axis will still be time. A lot of times, you'll also see that as distance divided by time squared. So it might be feet per minute squared there. And we almost always call acceleration a of t. So, let's look at a problem. It tells us that an object moves along a straight horizontal line. I'm going to make this a little bit larger. A straight horizontal line, so that at any time t, 0 is less than or equal to t less than or equal to 9, its position is given by x of t equals 9 minus 3t plus t squared. What is the velocity of the particle at t equals 5? Is the particle moving to the left or the right? So if we're wanting to know the velocity of a particle at a specific time, we want to know the slope of the graph, the rate of change of the graph at that point. So that means we need to take the derivative. So here, to take the derivative, I'm going to do x prime of t, and I'm also going to say this equals v of t, so that equals our velocity graph. And if I take this derivative, this is a very simple derivative. It's just going to be negative 3 plus 2t. And so if I want to know the velocity at t equals 5, I just need to plug 5 into this. So v of 5 will equal negative 3 plus 2 times 5. And I will have negative 3 plus 10, which will give me 7. So our answer here is 7. The question also asks if the particle is moving to the left or to the right. And so if velocity is positive here, the answer is going to be right. If velocity is negative, the particle would be moving to the left. This also asks me for the acceleration of the particle at t equals 5, and I want to know if the particle is speeding up or slowing down. So if I take the second derivative of t, or that's the same as the first derivative of velocity, or I'm going to call it a of t. If I take this derivative, I'm just taking the derivative of negative 3 plus 2t, which is just 2. And so really doesn't a of 5 is going to be the same as the acceleration at all points. It's just 2. Okay, and so here, this is our acceleration, very straightforward to find. But it wants to know if the particle is speeding up or slowing down. And so a lot of times students want to automatically say if acceleration is positive, you're speeding up. If acceleration is negative, you're slowing down, which seems to make sense. However, it is not the case. The reason that seems to make sense is because typically when we think of acceleration, we think of being in a car. And so if we know that we are in a car and we are accelerating in a positive manner, then that means that we're speeding up. So that's the force that throws you back in your seat whenever you take off really fast. And of course, deceleration would be when your acceleration is negative, and that's when you slam on the brakes and slow down. So all of that is assuming that you're moving in the positive direction. If you're moving in the negative direction, then it's not the case. So this is a little bit backwards. I mostly just have to think about the rules for this. It doesn't make a whole lot of sense. So if you are speeding up, or if your speed is increasing, v of t and a of t have the same sign. And if you're slowing down, v of t and a of t have different signs. So, if you think of what's happening here, we have a positive velocity. We also have a positive acceleration. So this particle is speeding up. If we had opposite signs there, if we had a negative 2 for acceleration, then the particle would be speeding down. Or if we had a negative velocity, if we had a negative 7 and a positive 2 for our acceleration, the particle would be slowing down. So it's not whether or not the acceleration is positive or negative, it is whether or not you have the same sign as your velocity. All right, let's keep going. So we've got this equation. It gives the position of a particle moving along a straight line at time x for 0 to 20. Find the time for 0 to 20 at which the particle is at rest. And so these are questions you're going to see often. The particle is at rest. And if the particle is at rest, it means it's not going anywhere. If you think, what is your velocity when you're not going anywhere? This should tell us that velocity equals 0. So in order to be able to find this, we are going to have to find our velocity and set it equal to 0. So to find the velocity, we need to do a derivative. So f prime of x, or I'm going to call it v of x, is going to be the derivative of a exponential is itself, so e to the square root of x. But you have to use a chain rule here because you have to multiply this by the derivative of the square root of x, which, remember, square root of x, this is like we're doing ex to the 1/2. So that would be 1/2 x to the negative 1/2. So you got e to the square root of x times 1/2 x to the negative 1/2 minus 4 here. And so if we clean that up just a little bit, That's e to the square root of x over 2 times the square root of x minus 4. And we want to know when this equals 0. So we're going to set this equal to 0. And so this is a problem that I could, I'm not even sure if I can do this with my hand. I'm not going to try to do this with my hand. I want to go over here to my calculator, and I'm going to say F2. And the first option there for F2 is solve. And I'm just going to type my equation in. You got to be careful with this. Make sure you put parentheses around your numerator and around your denominator. So you're going to have e to the square root of x. So notice, square root of x. And so, square root of x. Okay. So notice when you opened the square root, that opened a parentheses, so you got to close the parentheses for the square root. When you did e to the, it opened a parentheses, so you got to close the parentheses for the exponent there. And then you also have parentheses around the numerator that you started right here, so you got to close one more parentheses. And then this is going to be divided by, we're going to open another set of parentheses for our denominator. So we'll have 2 square root of x. You have to close your parentheses for your x and close your parentheses for your denominator. And we're going to say minus 4 equals 0. And then for this, we have to put a comma x so that the calculator knows what we're solving for. And we'll hit enter. And it tells us, warning, more solutions may exist. But we are getting 10.6386 or 0.020858. So we actually have two answers for this. So we've got x equals 10.63, I'm going to go with 639 here, and x equals 0.021 for that. So those are our 2 points at which the particle is at rest. And you could check this by plugging those numbers into your derivative to see if you do, in fact, get 0. The next question says, what is the position of the particle at x equals 0? So if we're asked about the position of the particle at x equals 0, we're just plugging into our position formula. So we're just finding f of 0. And since this is a calculator active problem, or I'm making it a calculator active problem, I'm going to do this. I'm going to show you something cool the calculator will do here. So I'm going to go here and I'm going to type in this function into my y equals. You don't have to do this, but I'm going to show you a reason that it makes it a little bit easier. You also could have used it to take your derivative. Because I can see that this next question asks me for position at x equals 20. Since this is in y1, if I do y1 of 0, it'll plug 0 into that equation for me. And I get 6. Actually, I don't need a squiggly equal sign because that is exactly 6. And then if I want to know, it says what's the position of the particle at x equals 20, y1 of 20 is going to be this. I'd rather have a decimal, so I'm going to hit the green button before I hit enter. So f of 20 is approximately 12.5435. I'm going to keep that whole number there. So D says, what is the total distance that the particle traveled on the interval from 0 to 20? And so this problem seems like if at 0 you're at 6 and if at F you're at 20, it seems like then you should just take these two and subtract them. However, that is going to tell you how far the particle is from where it started. So, for example, if you're sitting in my classroom and you ask to go to the bathroom, and I say sure, and you go walk to the bathroom over there near the stairwell, and they're cleaning the bathroom, and you can't go to that bathroom, then you're going to go walk back down past Coach Wood's room to the other bathroom there in front of Mr. Poplin's room, and you're going to go to that bathroom and then come back. So the distance that you traveled is a lot further than your displacement, because it's not just the distance from my room to that bathroom, because you went to the other bathroom first. So that's sort of what's happening here. So I am going to look at what's happening here by looking at this graph. And I want to change my window here so that I can see this from 0 to 20. So if I go to window, and I'm going to go from 0 to 20, and now I'm going to graph. And I really can't see what's going on here very well. So if you'll do F2, and once you've got your X right, if you'll do zoom fit, which I think it is it's A, zoom fit right here. Look out ahead. It's working. It's going to give me a picture of what this graph looks like. And you can see here that this particle was positive, then negative, then positive. So it changes directions here. So even though it was right here at 6 at f equals 0, and it ended up here at 12.54 at f equals 20, it traveled a lot further than that. So this is how we figure out what happens. We need to look at the derivative. So if we look at the derivative, that derivative again was v of x equals, we had e to the square root of x over 2 square root of x minus 4. And we set it equal to 0, and we found out that it equals 0 at 0.021, so really close over here, and again at 10.639. And so if we think about what's happening for this derivative, if the derivative, or if v of x is positive, that means that we were going to the right. And if v of x is negative, that means we're going to the left. And so these points right here where the particle is at rest are important, because in order to change from going to left to right, you have to have a velocity of 0, because if you're going to the right, you have to stop and turn around to go left. So we were going to the right or left here, and then we switched, and then we probably switched again. So so we could plug in some numbers here into this derivative to see. I'm going to go back here. So a number between 0 and 0.021 is very small. And I'm going to type it in this way. I'm going to do derivative of y1 of x. So the derivative, because I've got that function, comma x, such that x equals 0.01. Notice I get a positive number here, so I was going to the right. If I plug in a number between 0.21 and 10.6, so let's just use a 5. Let's hit the green button before we hit enter. We get a negative here. I bet if we pick a number between 10.639 and 20, we'll get a positive. we pick 13, little green button, we get 1.1, so it's positive. So we're going right, left, and then right again. So we know at 0, our position is 6. We've already found that. We know at 20, our position is 12.5435. What we need is our positions at 0.021 and 10.639. And so if I do that, I can just, because I've got it in y equals, it's so helpful to have it in y equals, I can just do y1 of 0.021, and I'm going to get 6.07194. And so the particle went to the right just a teeny tiny bit right here. If you think about how far that particle traveled, it's just that 0.07194. And then if we type in our position at 10.639, we're going to get negative 11.4609. And so the difference there, if we take that number and subtract the 6.07194, you went down 17.5328. Don't use the negative there because it doesn't, distance doesn't need to have a correction. And then here, to go from negative 11.4609 to 12.56, we would have negative 11.4609 minus 12.5435. That is going to give us negative 24. Actually, don't use the negative, 24.0044. And so if we take all these and add them together, here, let's add the 17.5328 and the 0.07194. We are going to get, oh, that was negative. Let me go back up here. Go back and get rid of that negative. Right, so we'll get 41.609 units there. So for this problem, you've got to think about where you're moving for this. So let's move on. Alright, so for this problem, we have the particle is traveling on an x-axis, has a position of x of t at time t. This graph is the velocity, and it wants to know which of the following expressions gives the total distance traveled by the particle over the time t 0 is less than or equal to t less than or equal to 5. So, if we want to know how far the particle is from when it began, we would just take x of 5 minus x of 0. This would be your displacement. But this just tells us how far you are from where you started. It does not tell us if you left Mrs. Hyatt's room, went to the other bathroom, had to turn around and go back to the one by Coach Wood's room. So this just tells you how far you are from the start. So if we look at what's happening here, we can see that our velocity is positive up until we get to 2. And then our velocity is negative all the way to 5. So that tells me from 0 to 2, I was going to the right. So my x of 0 to x of 2, that was going to the right. But then, from 2 to 5, so here's x of 2, right here is x of 5, I went back to the left. So what I want is I want these values to be positive. I want the distance that I traveled to be positive. So when I'm thinking about this, I'm going to the right. So x of 2 is greater than x of 0. So I would say x of 2 minus x of 0. That gives me how far I traveled while moving to the right. Now, I can't say x of 5 minus x of 2 here, because if I do that, I'm taking a smaller number and subtracting a larger number, and I'm going to get a negative here. I don't want a negative distance. I want this number to be positive. So if this is positive, then I'm going to have to take my bigger number, which is x of 2, and I'm going to have to subtract x of 5. And this will give me the total distance that the particle traveled. So this would be our expression here. The ones that you're going to see on your assignment will be multiple choice. So you're looking for what will give you a positive for those. Let's keep going. All right, so here the particle moves along the x-axis so that at any time t is greater than or equal to 0, its velocity is given by this equation. At what time is the particle furthest to the right? And so in this case, this is a fairly complicated velocity. I'm going to use the calculator for this. And we're going to look at this graph. So I've got negative 2x plus 20 square root of x plus 3. Square root. Fix that. Square root of x plus 3 plus 8. And so if I look at the graph here, I'm not really seeing anything. It's probably my fit for the graph. I am looking for t greater than or equal to 0. So this is already looking at the positives. I'm going to hit F2 and then zoom fit, which is right here. It's A. And so if we look at our velocity here, we can see that this velocity is always positive. So since this velocity, actually, it's actually not going to be always positive. Let's change our window a little bit. Let's go. We need a lot bigger numbers, so let's go to like 150 here and just graph and see what happens here. Now, I know this because I am looking at my notes here. Another way you can know that this is eventually going to go back down, if you go to your table and you look at your numbers, let's see, my table is set up where I have to ask. Let's go to independent. Let's see. If we go to table set, oh no. Oh, let's see, go back to table, to F2, which is set up. And then instead of ask, go to auto, and I'm going to, instead of going up by 1, I'm going to go up by 10, just so you can see the numbers more quickly. On the 89, you have to hit enter for this. And so we're going to go to the table, and you can see your numbers are going up. They start to come back down, and then you can see they go negative here. So if I go back to that graph, so that's how you can know you should go out a little bit further. If we go, this time zoom, fit, oh, lost it. So if we look at this, our particle is moving to the right whenever our velocity is positive. And then it moves to the left whenever it becomes negative. So our particle is moving to the right, 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 right. And then right here it switches and it moves to the left. So it's got to be furthest to the right, right here at this point. So if we want to know that point, we're going to do F5, which is math. And we want to find the 0. And so we can use that as our lower bound. Our upper bound, we have to go up here, go past that intersection. And you can see we get 110.569. So we could say at x equals 110.569 for this. All right, got a couple more. So the particle moves along the x-axis so that anytime t is greater than 0, its position is given by this equation here, where a is a positive constant. At what time t is the particle's position furthest to the left? And so if we take the derivative here, we would need to use a quotient rule. And so we'd have t times the derivative of e to the 2at, which is going to be e to the 2at, times the derivative of 2at, which is going to be 2a, minus e to the 2at, times the derivative of t, which is 1, all over t squared. And so let's clean that up a little bit. I'm going to factor out that e to the 2at. And then we'll have 2at minus 1 over t squared. So that gives us our derivative. And so I want to know when the particle is going to be furthest to the left. And so to think about what's happening here, I need to think about this derivative and whether it's positive or negative. Now, I can't use my calculator on this because I don't know the a. But what I can do is I can think about the signs of this. So what I'm going to do is create a sign line. And so if I get 0 in the numerator or denominator, it is going to give me a point where possibly I switch from positive to negative on this velocity. So I want to take each piece. I've got e to the 2at. I'll set that equal to 0. I've got 2at minus 1. I'm going to set that equal to 0. And t squared. I'm going to set that equal to 0. And e to the 2at, if I take natural log of both sides here, I can't take natural log of 0. E to any power is always positive, so you don't get any answers from this. Right here, if you're solving for the t, then you would move the 1 over. You got 2at equals 1, and you would divide both sides by 2a. Because remember, a is just a number. And you get 1 over 2a. And in here, t squared, you just get t equals 0. But we're looking where t is greater than 0, so that's not really going to help us a lot either. So the one place where my derivative is going to switch sign has got to be right here at 1 over 2a. And it does tell me that a is a positive constant. So I do know that a is a positive number. So here, if I'm trying to think of what I need to know is when this is going to be positive and when it's going to be negative. And so if I know a is a positive constant, that really doesn't tell me what value a is. A constant could be a fraction, it could be a decimal, it could be a whole number, but I do know this is positive. So if I'm thinking of a number that is smaller than 1 over 2a, I could pick 1 over 3a. Because that denominator is going to be larger, which is going to make it smaller. So if I plug in 1 over 3a into my derivative, I'm going to have e to the 2a times 1 over 3a, 2a times 1 over 3a minus 1 over 1 over 3a squared. Now, if I think about what happens here, this right here is going to be positive because e to any power is always positive. This right here, since a is positive and I'm squaring this, this is also positive. So what I really care about is the sign of this right here. So I could put this over 1. This is going to be 2a over 3a minus 1, which your a's will cancel, so you'll get 2/3 minus 1, which is negative 1/3. So you get a negative in the section. And so if you're thinking of a number that's larger than 1 over 2a, you might be tempted to use something like 1. But if a is 1/5, then this is actually bigger than 1 already. So what you've got to use over here is 1 over a. And so if we plug in, again, the same thing's going to happen with your e and your denominator. It really only matters about this 2at minus 1. So if we do 2a times 1 over a minus 1, then we're going to have 2a over a minus 1. The a's will cancel, and we'll get 2 minus 1, which is 1. So we get a positive over here. So we can see that at this point, this is our velocity. And at this time, the positions particle is furthest to the left because we switched directions from left to right. So we would say at t equals 1 over 2a, the particle is furthest to, I think I said right before, to the left, because it changes direction from left to right when the derivative, or velocity, changes from negative to positive. Alright, so we've got one more that I want us to look at. So we've got another function. This gives us the position, and this is for whenever t is greater than 1/2. We're supposed to write the equation for the velocity of the particle at time t. Is the first thing we're supposed to do. So, I was going to do that by hand, but I've changed my mind. Let's use the calculator on this. So I'm going to type in the calculator here. I'm going to use the x instead. X times, now right here when you're doing sine of 1 over t squared, you have to type it in like this. You have to do sine of 1 over x, over x, and then close your parentheses that goes around sine and square that so that it looks like so. No, I've got too many parentheses. Hold on. Alright, so I do not need this parentheses at the beginning. And I've got one too many here at the end. Let's try that. No, still wrong. Okay. Alright, x times sine of 1 over x. Close the parentheses for the 1 over x. Close the parentheses that's in front of sine. Raise that to the second power. Okay, that looks better. This is what we're looking for here. And so to take this derivative, if you go back to the home screen, you can just type in F3, differentiate y1 of x and comma x, and it will give us the derivative. So you can see that your v of t here is going to be sine squared of 1 over x minus 2 sine of 1 over x cosine of 1 over x over x. And I think that's all. Let me move up here to make sure I didn't miss anything. Yes. All right, so that is our velocity. And B is going to ask us at time t equals 3 over pi, is the particle moving toward the origin or away from the origin? Give a reason for your answer. And so you've got to know two things for this to happen. First of all, you have to know where the particle is at 3 over pi in the first place. So to find that, you're going to have to do y of 3 over pi. And since I've got this in the calculator already, y is already in there. So I can just do y1 of 3 divided by pi. And my division didn't. All right, okay, there we go. And it's going to give me an answer, probably an ugly answer. No, not too bad. 9 over 4 pi. Okay, so that is my answer for where the particle is at. This is on the y-axis. If you want a decimal for that, you've got 0.716197. So we're at a positive position. And so in order for this particle to be going away from the origin, it would need to be moving up. If it was going towards the origin, it would need to be moving down. That would not be the case if this was negative, so you need to know this. So we also need to know our velocity at 3 over pi. And so to find this in your calculator, the quickest way to do this is to do that derivative that we did just a minute ago. Derivative of y1 of x, comma x. And don't plug this in by hand. Do such that x equals, you might need some parentheses here, 3 over pi. And we get this stuff, let's just go with a decimal here. And we get negative 0.1569. In this case, because we're on the y-axis, a negative velocity means that you're moving down. And so if you're at a positive position and you're moving down, you're going towards the origin. Okay, so this has been a little bit of long notes, but hopefully you were able to follow. I know that you might have some questions. If you do, we will look at this in class on Monday. So please do the assignment that is in AP Classroom. If you have questions, you can let me know, and we will, like I said, we'll review this on Monday if we need to.